All right. So, if you look in Canvas, I've uploaded a new data set called study data. We're going to be working with this particular data set today. We're going to be using Minitab to do it all. So, at some point, we're going to start getting to that. But again, we're going to be doing a logistic regression, and same thing as we did last time. Upload the data. We'll work through a bunch of the different options. You're going to write any of the variables that you found that are statistically significant up on the board, and then we'll have a discussion about that. Uh, Tonight or today, when I go back for my office hour, I'm going to write up a couple different homeworks for all of you to handle. And basically, you're going to do linear regression and logistic regression the way we've been doing it in class. But what I'm going to have you do is instead of every single one of you doing, say, the same or doing one analysis, I'm going to have you do 5 different ones. You need to report back to me what random seeds you chose. Then what are the statistically significant variables. Once you've got that, uh, if any variable appears 4 or 5 times, we're going to turn this into a little bit of a competition, say with the data. So if you have a variable that appears 4 or 5 out of 5 times, we're going to assume that that's good enough, or that's a sign that this variable actually does belong. You're going to go back, use only the variables that appeared 4 and 5 times, then analyze the data using just those variables, and then report back what variables did you find that have p-values that when you look on Minitab are say 0.000, what are in the range of 0.01 to 0.001, and then you'll also have 0.01 to 0.05. So we can see what variables seem to be the most important or the most significant, and what seem to be, say, the least significant. And with everything that we do, again, the way that this is, or the way that we're going to be analyzing the data, uh, go into Minitab, you can import the data. Study data, I actually don't think it matters which one to use. So this is showing me all the different columns of data that looks appropriate to me. So I'm going to go ahead and click on OK. And now to move this up a little bit. So this time, what we're going to be doing, go to Stat, Regression, Binary Logistic Regression, and then Fit Binary Logistic Model. So it says here, response in binary response frequency format. Yes, it is. So just so we get some idea of what's going on here. When you look at the data, this is again something that I actually created. I want to look at Y05 _10. Response event, again, is going to be a 1. Continuous predictors are going to be this R1 all the way through W44. And what I did with this particular set of data is I went in, I created a model using R1 through R6. So again, this is uh, data that I made, so I know what's actually statistically significant in here. 44 other variables that are completely useless or have nothing to do with the data that we're looking at. And then I decided, okay, these are under what I created. These variables are going to be, say, event data. And then I added in some random data to create false positives and false negatives. So what's happening here is about 15% of the response data is going to be what's called event data. 5% of it is real, 10% of it is actually fake. So once we've got that set up, we're going to come down here to where it says model. Again, highlight all the different variables, and then add all the terms through second order. When you're dealing with the data for real, you have no idea what the actual model is going to be. You have no idea what interactions might be important. You have no idea if a response is going to be linear or quadratic or anything like that. Because the way that we're doing this, we're looking to see maybe is there something in there. We're not any variable or any term that is not determined to be statistically significant will be eliminated. But we're at least going to take a look. We're at least going to see. When you do that, you do increase the chances that you're going to have some more spurious correlations in variables that look important but really aren't. But you can also find that there are actually things going on that you might not have thought about. For right now, we're going to go to stepwise. And I'm going to change this to stepwise. And I'm going to change alpha to enter and alpha to remove to 0.1. And once I've done that, I can go ahead and click on OK. Head over to validation. Again, validation method, validation with the test set. For right now, we're just going to keep it as is. But when you go to write things up on the board, you have to change your random seed, which is right here. So whatever 4-digit number you used last time, you can use that again this time. I'm just going to keep it as is. I'm not going to worry about it for right now. Going to go ahead and click on OK. And one of the other things that if we're dealing with logistic regression, we were talking about it on Tuesday. What we're doing is we're trying to figure out what is the probability that under these sets of values for each variable that say particular person or that particular vehicle is going to be an event data. Minitab, for whatever reason, doesn't give you that table that we're talking about where you can look at the true positives, true negatives, false negatives. But if you go to storage, you can see up here where it says fits. So we want to fit the event probability. And then I'm going to come down here and click on OK. And then come over here and click on OK. And then we wait mere moments. And I will say for the homework, uh, once you've got it set up for the first analysis, the homework should take maybe 20 minutes. So 20 minutes each one. So I would try and do it all, say, in one day, as opposed to doing a little bit of it one day, coming back, doing a little bit more the next day. So we can see what happened here. We can see the number of event data that was in training, the number of event data that was in the test, the total number of data between the two. So 30,000 data points. That's cool. And we look down here and you notice again, the VIF is way off the charts. But we also notice all these variables over here that seem to have come up as being statistically significant. So we know for certain R1 through R6 are part of the model. But try and open this up in Word so we can see it a little bit better, hopefully. All right. But at least looking at the data that I've got here, what variable doesn't seem like it's in the list? R1 through R6 are statistically significant. R1 through R6 are part of the model. What R variable is missing? R6. So this is, again, the type of thing that actually happens when you are analyzing data. The software, again, is looking at what variables seem to have the highest correlation with the outcome. I'm just writing down all the variables that we see here, R3, R4, R5, W9, W23, and W38. Now again, looking at the VIF here, looks like everything is well above 5, which is our cutoff point. So if you're using certain types of software, it won't even show you that. You can try to force the software to show you that, but it doesn't like to. And there's actually some software that doesn't have a function to show you that. So we know uh, that the VIF, when it is this high, is a sign that maybe things aren't as good as we'd hoped they would be. But looking at the rest of the data, so here's where we can see some of the odds ratios that I was talking about. So it says on here, because R1 through R5 and W23 and all that are used in interactions, it's not actually going to give us odds ratios, but it is going to give us a W9 and W38. And you can see that the odds ratio here is 86. So if we're to interpret this, or if, say, this was medical data that we're dealing with, you could say, based on our study, we found that there's a 14% decrease in whatever the event is, uh, based upon whatever variable W38 is. For the homework, you're going to have real data. For this, I'm just trying to show you what can happen and what will happen, and then we can go from there. So we can go back to stat, we can go to regression, binary logistic regression, we're going to fit another binary logistic model. So in Minitab, one of the nice things about it is I can go to where it says coding, and then we're going to standardize. But the way that we're going to standardize them is to subtract the mean. And then go ahead and click on OK. And pretty much everything else that we want is already going to be in there. So I'm going to go ahead again and click on OK. And this is probably the longest part, right? Just waiting for the computer to process everything. And I'm sure for anyone that watches these videos later on, this is going to make for some really great video watching, right? That's why you're all happy that there's the button on there that lets you play it back at 1.5 speed or two times speed. So it did what it's supposed to. Same amount or same data. And looking again at the model, what is the VIF that we've got here? Everything's pretty close to 1, which is what we want. So if you're going to try to do analyses like these in, say, a program like Python, there is no option to subtract the mean automatically and run a model based on that. You actually have to go in and create little lines of code that will subtract the mean from all the variables. Then you have to go in, type in all these new variables that you want to look at, and then do all this other stuff. But it does give you a really nice true positive, true negative, false positive, false negative thing at the end. Again, if you actually put that bit of code in there. And looking at the data that we got this time, again, what variables seem to be statistically significant here? R1 through R5, so we're still missing R6. And then W9, W23, and W38. So those variables all came up last time. One thing to notice, if you look at the coefficients for what you have now versus what we had before, so for like R1, the coefficient, once we've subtracted the mean from everything, is 0.08. Well, we had it, or the way that we had it before, it was negative 101 point, or negative 101.6. So when you, again, when you have these high VIF values, it can affect the coefficients. It can affect what actually comes up as being seen as statistically significant. So we need to be conscious of that. Using, or when we have the VIF again, right around 1, that is what we want, or one of the things we want from our models. Some of these other interaction terms, some of them look like they're the same coefficients, but for all of these, like right up here, looks like all of these have different coefficients than what we had before. So we were talking about it last time. Let's say we want to go in and we want to try to, say, optimize this. If we're looking at, say, a particular, or if we're looking at data again, and this is a disease, would we want to maximize disease or would we want to minimize disease? Probably want to minimize it, right? Unless you have unless there's some people on your I don't like them list, then you might want to maximize disease for them. But that's a you thing you need to work out. So you can go to stat, regression, binary logistic, and then come down here to response optimizer. And our goal here is going to be to minimize. I'm not going to worry about anything else that's on here. I'm just going to say we want to minimize that. Go ahead and click on OK. And you can see the different values we should be setting all of these variables at in order to minimize our chances of an event happening. So this is also going to be part of the homework, but this is going to be part of the homework once you've gotten rid of all the variables that we don't even need to bother looking at, optimizing the final model that you've got. So should we need it, it's actually there. If we want to make predictions on what's going to happen under certain conditions, with linear regression, with logistic regression, you can go to stat, regression, binary logistic, and then there is that ability to predict. So if you have, say, some new data you want to test out, you have to create new columns for all the different variables that you found to be statistically significant. I don't have anything set aside for this, so I'm not going to bother with it. But if you want to, you can put in new data in there and see how well your model continues to work on new data. For the project that I've assigned to everyone, one of the things that you're most likely going to find when it comes to, say, AI not doing a really good job, if the data tends to change over time, like say if we look at consumer preferences for something and it's based on data from say 2019, have consumer preferences changed since 2019? The answer is yes. Some of the if you work in the restaurant industry, uh, pre-COVID, you'd probably be a lot more packed than you are post-COVID, right? So so if you're using data from 2019 trying to predict what's going to happen, say 2025, 2026, probably not going to work out that well. If you're looking at stuff like, say, car sales pre-COVID versus post-COVID, automotive companies are making a lot more money now, but are they selling as many vehicles as they did before? Not really. A lot of people are buying more used vehicles and they're holding on to their vehicles a lot longer than they used to. So if you're looking at data pre-COVID and you're going to try to predict what's happening post-COVID, probably not going to work out too well for you. So this is just in case you need it. We've got the predictability here. And if we're going to do a regression, there's also, it's not highlighted because we haven't done anything with it, but we can also come up here and predict what's going to be going on. And then you've got the response optimizer. If you're trying to do analyzing some data, say for another class or for a presentation, a couple of the cool things that are on here too, we can do like a contour plot. So we can look at, so this is just looking at R1 and R2 together, or we can generate a plot for all the pairs and do all the pairs on separate graphs. Go ahead and click on OK. Once you've run your model and you've got it to where you're satisfied with it, this will work out pretty well. some of these contour plots kind of look a lot prettier than just a standard graph, don't they? So you can see when you're looking at some of these, like the lighter shades, we're looking at the Y value. The lighter the shade, the lower the Y value, so the darker green. So again, if we are looking at this data in terms of, say, a disease, or if we're looking at this data in terms of, uh, like with one of the data sets that I had, we're looking at vehicles that are coming back for warranty repair. Where do we want all of these things to be? We're looking in here, and there's some really light green in this huge area out here. The huge area out here is telling us what? That's kind of like a safe space. You're not going to have that high a disease when R1 is in any of these areas and R5 is between either of these values. So what's nice about this, or something like this, if we're looking at it, is we have a wide area to work with. So if you're in a production facility, if there is a little bit of drift on, say, R1 and R5, is it going to be catastrophic? Well, looking at the graph, what'd you say? 60% of the graph says it's going to be fine. It's just when things get up over here that you really start to have to worry about things. If we're looking at this event data and the event data is the thing that we want, we have to really, really control, in this case, R1, because you've only got that narrow band to work with. If something starts drifting too much, you're done. If we look over here, you can see again R1 when it's at one of its lower values, or sorry, at one of its higher values, again, is more likely to produce event data. But if you look at how it comes back to and plays with R4, you can see that you kind of need to make sure that they're in an even smaller area. If we're looking for to create events, if we don't want to create events, again, we've got this larger area to work with, which means as long as we make sure everything stays within whatever these parameters are, we should be good to go. And you can see the same thing with all of these. And now we got some blue. That so with all these different plots, you can go in them and you can start to get an idea about how much can something change uh, before we really need to be worried about anything. We can also do, and again, does anyone think that these plots look a lot better than, say, the traditional graph you make with Excel? Put a bunch of plot dots on there or whatever. We can go back to stat, regression, binary. If you want to do some really fun stuff, you can do a surface plot and do everything and do it all in separate graphs. If you put it all in one graph, it's going to be tiny. But I can go ahead and click on OK. Now it almost looks like you're dealing with some mathematical software like MATLAB or something like that. You can actually see what these shapes look like. So these are 3D representations of all those contour plots that we had. So if you want to go extra fancy, here's your extra fancy. And I'm going to scoot this up a little bit. And I'm going to scoot this thing all the way over. So one of the things I had all of you do was actually go in and do this fits thing. When you look at all the information that's in the column here, what this is trying to tell us is that, as an example, based on the model that we just made, we predict that, say, row 1 has a 23.9% chance of being an event data. So when I was talking on Tuesday about we can come up with these predictions, a lot of times the default setting is going to be, say, 50%. 50% and over, we believe it's going to be event data. 50% and under, it's going to be non-event data. And we can see what are the predictions for all of these things. In my public health classes, we look at these, and one of the questions I have for my students, and something like this might end up on an exam for all of you as well. Suppose the model that we just did, we're looking at, does the person have cancer? In a traditional model, or the traditional way of looking at it, anyone that scores above a 50% in this fits column, we're going to say we believe they have cancer and go forward with that. But if you look at this first person, let's say this is you, and there's a 24% chance that you have cancer. Would you want your doctor to say, there's a 24% chance you have cancer, we might want to watch this a little bit more closely? Or would you want your doctor to say, well, it's not above 50%, so they're completely fine? What would you guys want? If there's a 24% chance that you have cancer, do you want your doctor to say something to you? Maybe, maybe not. If we look down here, just looking at row number 13, there is a 6% chance at, and again, this data is nonsense, but if it was, say, health data, and we're looking at, do people have cancer? If there's a 6% chance that you have cancer, would you want your doctor to say something to you or not? Is there a certain cutoff where if it's below a certain percentage, you're not going to worry about it? Is there a certain value where you look at it, you could almost be certain that the person has cancer, or at least based on the model and the information that we have? So when we're looking at this type of data, and who knows, maybe you're doing something for your boss, and the event data that we're looking at here is, does a customer churn, meaning does the customer leave us for whatever reason? Boss man or boss ma'am might be interested in, there's a 1 in 3 chance that this customer might leave us. Do you think the boss would actually care about a 1 in 3 chance that they're going to leave? So a lot of different things we can do with this. If you are a skilled programmer, you can take that data, you can make the matrices that I was talking about. You can change the cutoff values to whatever you want. You can go back, you can calculate the accuracy of the models when you change everything. I believe if you take the data science class, if they use the same software that I did when I took a similar class, uh, it's all done in Excel, and there's actually like a little thing where you can change the cutoff really quickly and see what the results are. And a lot of this stuff is actually automated for you. So we've got the information here. We can take this information, use it basically however we want. And we can also think of this as this entire column here is the predicted outcome for each one of our rows of data that we have. Okay. So for all of you, head on back to stat, regression, binary logistic, fit binary logistic model. This time, the response variable we're going to use, let's go with the Y1010, so C61. Since we've already got everything set up the way that we need it, we're pretty much done. We're going to be modeling, oh, we have to, sorry, come back here, highlight all the predictors, and, oh, is it already? Okay. Heck, it's already doing that. Cool. Don't even need to do that. Sorry. So the only thing that we really need to do here is go to validation, change that random seed to what? Here. So everything should be ready to go. The thing that I changed is the response, instead of being Y05 or underscore 05 underscore 10, we're just going to do Y1010. So 10% real data, 10% random data. And there are going to be some false positives and some false negatives here. So once we've got that, go to validation, put in whatever your 4-digit random number is going to be, and then click. So that goes in right here. Going to go ahead and click on OK. And then everything else should be set up. So you should be able to go to where it says OK. Wait while it does its thing. And then you're going to get some results. I'm going to get some results. We're going to write our results up on the board again. And does anyone remember the uniform distribution from your DS301 class? Okay, so that's a thing. That's a total mess. I'm gonna get to that later. Yeah. So it looks like I've got the variables popping up that I need to look at. And according to my model, I've got what? R1, 2, 3, 4, 5. And then what? W9, 17, 18. And W23. Write down what you guys got and bring it on up. Anyone get an R6? One person got an R6. All right. Two people. Let's see, R1.
Could be. Could be. I might have wrote it wrong.
Well, usually R1 is one of the things that always pops up, which is why I'm wondering. It is possible that it should be there. I'll check it. Bummer, where's on here? Was that it?
If
Hmm?
I've scrolled down too far.
So again, with the homework, it's going to be on all of you to choose 5 different random seeds, whatever 5 4-digit values you want to use, go ahead and use it. They're going to get results similar to what we have up here. To make it a little bit easier, let's say these are the 5 results that you get, okay? So I'm not even looking at mine. Let's just say this is what we got. What do all of these have in common? R1, R2, R3, R4, R5. So I've got a W11, 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 W11. So that's 5 out of 5. W1, that only appears there. W13 and 14. No, no. So W13 appears 3 out of 5 times, not good enough for what we're doing here. W23, 23, 23. No 23 here, but we got a 23 here, so that's 4 out of 5. Uh, 28 only appears once, 27 appears 2 times, 28 appears twice, 27 appears 2 times. 35 and a 35 and a 35, so that's 3 out of 5, not good enough. So let's go with just because this is going to be like what you do for the homework, okay? We're going to go back. Out of 50 variables, we've whittled it down to 7. So go back to stat, regression, binary logistic regression, fit binary logistic model. For our predictors, if it's not on the board over there, let's see. So R6 does not appear. We can eliminate, oops. Sorry, doing this the wrong way. So double click on R1, R2, R3, R4, R5, W11, and then we've got W23. So for this one, because we changed the continuous predictors, we probably do need to go back to model. Highlight everything. Oops. Set that to default, I guess, and then highlight everything. So to get rid of everything that was down here, I just hit the default button. Gonna do everything through 2 terms. Go ahead and click on OK. And since everything else is set up, I'm gonna go ahead and click on OK. And that took that one a lot faster, didn't it? So looking at what we have here right now, at least for me, all of you have your different random seeds that you used. But this is telling me round 1, we looked at 5 different, or the same data set 5 times with 5 different random values or random seeds. We went from 50 variables down to 7. Those 7 are now competing with each other. And I've got R1 through R5 and W23. So those would be my statistically significant variables. R1 through R4, the p-value is 0.000 all the way through. R5, the p-value would be in that second column of 0.001 to 0.01. And then W23 would be in that third column of 1% to 5%. So what are the actual factual important variables that are used here? R1 through R6. We got 5 out of the 6 we should have. We've got 1 extra one. Is that a lot better than, say, the models that everyone else got, where everyone has looks like between 3 and maybe 6 of these spurious correlations? So again, some of the things that will happen when you do these things for real, you could actually miss out on something that is or should be part of the model. If we have too much variability, or it's generally called signal to noise ratio is a bit too low, you might not find it. In this case, we went from like I said, 3 to 6, 3 to 7 spurious correlations down to only 1. So that's a major improvement. For those of you that think about things in terms of, did I do it right or did I do it wrong? Well, we just did it a whole lot better than any one of us by ourselves, right? So did any of you get a W23 showing up as significant on your data sets? So think about that. With the 5 random seeds we had there, W23 came up every single time. But when we eliminated a lot of the other competition, at least for me, sorry, I mean W11. But anyway, one of those variables wasn't able to hack it when it came down to, like, say, the final whatever. So if we can eliminate these spurious correlations whenever possible, it's always a great thing to do. Unless you take the data science class, you can do what we've done here to eliminate spurious correlations. when you take the data science class, you can do the same thing with all the different models you learn in there and hopefully come up with, say, the best of the best, and then go forward and use that. An example of uh, where we want, where some of these things might actually be important. When I was looking at a data set that I got from an automotive company that used to have their world headquarters in Auburn Hills. Not a lot to mention any names because I don't remember what their name is right now, anyways. One of the things that happened is if I was to look at one of those plots that we did, you would find that initially there were like 400 vehicles that had come in for warranty repair out of 120,000 vehicles for over 12. So that's going to be basically 1 in 300 vehicles that was produced has already had some sort of a warranty issue. Some of the variables that we had for sure was a torque on like a nut 7 or something like that. And literally with the data set that I had, uh, we've all seen a vehicle before, right? We all know that there are lug nuts that go on each tire. Some of us have 4, some of us have 5, some of us have 6. Some of the variables I'm working with were what is the torque on each one of those lug nuts for every single vehicle and every single nut on every single one of those vehicles. What is what's called camber, which if you look at your tires, if your tire is going straight up and down and it's perfectly straight up and down, your camber is 0. If you're into a drifting, you want to have your tire camber set so that the bottom of the tire actually comes out. And I honestly don't remember if it comes out from the wheel well, that's positive, or goes into the wheel well, that's positive camber. But the other thing that we needed to look at was whatever the camber was on, say, wheel 3, and then torque on a certain nut. And when it was between whatever these values are, so we've got literally 1,000 vehicles that are within this range. So they're just like all over. There were uh, basically 40 of them that were within these ranges, and probably picking green versus black, not the best idea for at least for this monitor. But anyway, 40 of them within those ranges were vehicles that had come back for warranty work. What does the camber on whatever tire it is and the torque on a nut have to do with, say, ride quality? If what we just found here is factual and true, you can now go in and you can literally tell all the guys and gals that are working on the line, when you go to torque nut number 7, whatever it was, it can't be within whatever the range is for A and B. Still got to be within spec. It's just it can't be within that smaller range right there. And and again, if this is true, we've explained why 40 vehicles have come back for warranty repair, which means there's about 360 other vehicles that we might be able to come up with accurate predictions on. We might not. But if you can reduce warranty repairs by 10% by changing the torque on a nut, is it worth it? You all had better be shaking your heads. Hell yeah. Yes, it is. If one of those two, or if what we just found here is one of these spurious correlations and it's just bogus garbage, how much time and money does it take to retorque a nut that might be within that range? And you two were talking about going to the Ford assembly plant, right? So when you watch them torque the nuts, how long does it take them to do that? Yeah. So in this case, if we're if this is if we recommend that they make sure the torque isn't within whatever that range is, and everyone on the plant goes through and make sure that the torque on whatever nut that is not within those ranges, it takes an extra second, 2 seconds. If it's real, you just eliminated 10% of your warranty claims. If it's fake, you just spent an extra 2 seconds. 2 seconds of a time for a person working on the line. Is that a significant cost? Even if they're making $100 an hour, is 2 seconds on the line a significant cost for one worker or one position on the line? Absolutely not. So in this case, if it's real, we just eliminated 10% of the warranty claims. If that is false, we spent minimal amount of money chasing a ghost. Now, if we're looking at something else, and let's say we're looking at, did someone get, say, a full body MRI? Anyone have any type of MRI before? To get one of my knees looked at one point, it was $30,000. Full body scan, going to be a whole lot more than that. But let's say you've got a data set, you happen to be working at a hospital or you happen to be working at an insurance company, and let's say the hospital runs their model and they find out that a full body MRI scan is really helpful for predicting whether or not someone has a disease. But when you do your model at the insurance company, you don't find that's happening. What is the insurance company going to do when the doctor orders that full body MRI scan? They're going to deny it, right? Hospital says it's valuable. The insurance company, using the same data set, can literally come back and say, no, it's not valuable. Why is that? Well, you're just looking at what's happening up here. How many of you had exactly the same results as anyone else? You didn't. Which is why I'm saying, for the homework, you're going to go in, you're going to run 5 different random seeds. You're going to tell me what random seed you ran and what variables came up as being statistically significant. And anything that came up 4 or 5 times out of 5, put them into like a final tournament, let them battle it out. Then you can tell me what is actually the best thing to do here. And then the final step, we can go back, stat, regression, go right back to the response optimizer. And since we did a couple of these, I'm gonna have to change that. So again, let's say we're using data Y1010, and let's say event data is cancer or something like that. We want to minimize that. Go ahead and click on OK. And those are the different settings that I want to try to have for all of these things. or try to get them as close to that as possible. So, oh, and if you look down here as well, uh, looking at the fits for some of these terms, some of them change a little bit, some of them not so much. That's kind of expected. So even if you have, unless you have a model that is choosing a whole bunch of variables that really don't belong, any one of the models would be pretty good at predicting what the outcome's actually going to be. But the better the model we use, the better our prediction's going to be. The better our prediction's going to be, the better the chances are that we will actually have or get the right answer. So everything that we've done here in the last, what, 30 minutes of class, that's going to be the homework. So when I say it should take about 20 minutes to do each one of them, I'm actually not kidding about that. I want to look up something real quick. I got an email confirmation yesterday about when our uh, final is going to be. Just trying to find it right now. So our final in this actually will be in class. I know you're all disappointed. I'd rather stay home, but whatever. So the final is going to be December 16th, 3 to 6 p.m. and in this room. So a little bit different time than our usual class period. So if you do need to get that time off from work, you've got a little over a month. And and I'll make an announcement about that so that you have it like on a permanent record. So you can tell your boss, yeah, I can't work on this day at these times. And then hopefully they will actually give you that time off. So no one ever had issues with that where you tell the boss, hey, I've got a final exam on this day at this time. I can't come in and they schedule up at that time on that day anyways. Even if it's normally a day you get off, it's like they specifically schedule you to be in a day when you said you can't be there. Anyone else have that happen with their? So at any rate, uh, that's when our final is going to be. It's going to be in this room, and it's going to be similar to the material you've got on exam number 1 and 2. Uh, which means next week we are going to be going over forecasting. Then we're going to have a Thanksgiving break, which you can all use to study. And then on Tuesday of next week, after Thanksgiving on that Tuesday, uh, do a quick review for the exam. I'll give you the exam. You take it home, bring it back on Thursday, and then we'll start working on a review for the final. Does that sound good? Get you in a second. All right. You have to take the final blindfolded in a dark room with spiders and rats running around. No, because I said so. I will have graphing calculators uh, for anyone that needs to use them, because there will be questions about tests of proportions. There will be questions about t-tests and stuff like that. As far as like ANOVA regression models and stuff we've been doing, uh, you'll need a scientific calculator for that stuff. It'll be just like what we've had in the homework. So if you're fine with the homework, you should be fine on the exams. Yeah, probably 20, maybe 30. One question, yes or no, explain, prove. And if you get it wrong, you get nothing. If I don't like something, you get nothing. You misspell a word, you get nothing. If you can't properly read my mind, you get nothing. So you keep asking questions and I keep giving sarcastic responses. Do you really expect to get anything different this time? Good luck with that. Let me know how that works out for you. Sure. With if when you look at everything, it's going to be basic math or it's stuff that you're going to be using a calculator with. So you don't really, if you want to have a sheet where you write down a formula you don't need because your calculator is going to do it for you. Do you really need that type of information? No, I'm actually being serious this time. Yeah, there's with with the homework with the Onanova, that's that would be about the only thing where, well, that and chi-squared would be about the only thing where uh having like a cheat sheet would be useful. But after you've done all those problems, you should know how to do it anyways. So
So just to clarify, there's only the exam one, we already did the AI essay and then the final.
in the two labs. So we're not going to actually get up to the 1,000 points that I had originally planned, but you will be graded based on all that everything. And you've got like what, about a month to get that 3 to 5 page essay. So no, that's not too much of a task, is it? And which of course means what? Everyone's going to wait until the day before and then try to research all this stuff, right? At least some of you are honest. I mean, well, the lab points are going to be part of the homework. So you can think of it as 2 more homeworks. All right.
This is just with my computer, but only coefficients show up. Instead of coded coefficients, they're bringing computer.
So you're talking about on here. So you should be getting coefficients.
Coefficients.
So yeah, those are the coefficients. So if you scroll up, not that far. Did I break your computer
No.
again? So looking what you have, R1 through R5, W11 and W23. Got the coefficients there, and you've got the p-values over here.
Okay, even though this is just straight up, it doesn't say coded, it's fine.
Well, you need to make sure that you properly chose. So how do you get decoded? Go to stat, regression. You can look up there, it should be a little bit easier. So when you go to fit the binary, you have to click on here where it says coding, and then change that to subtract the mean.
Okay,
And you can, this will be uploaded so you can
yeah.
kind of follow along a little bit better. All right. So that's all I've got for today. Door is over that way. Please go through it.